Hopefully you recall that the Z-score is the standard score used most frequently by researchers, and that Z-scores are useful for comparing individual data points within a dataset. But knowing the concept is not enough. You also need to know how to calculate Z-scores. This video will focus on explaining the Z-score formula, how to calculate it, using a critical value table to convert a Z-score to a percentage, and then understanding the relationship between a calculated Z-score and a critical Z-score, or what it all means. As you may know, you could see the Z-score formula written in a variety of ways, depending upon if you are calculating Z-scores in a sample or in a population. They mean the same thing, and you calculate the Z-score the same way. The score you are interested in minus the mean of the distribution divided by the standard deviation of that distribution. For this discussion, we'll assume that we're working with a sample, so let's stick with this one. A score, identified as x, minus the mean, denoted as x bar, divided by the standard deviation. This means that you need three things to calculate a z-score. The score, obviously, that you want to standardize or convert. This is often called the raw score to distinguish it from the score that you'll end up calculating. The mean, or the arithmetic average, for the data set, and the standard deviation for the data set. Then, if you want to convert the z-score to a percentage to determine what percentile that relates to, you'll need a z-score critical value chart. Just a few things to keep in mind before we do an actual calculation. Remember, the standard deviation part of this formula will always be positive. The z-score, however, could be positive or negative. What causes the z-score to be positive or negative happens in the numerator. If the raw score is below the mean or less than the mean, then the z-value will be negative. If, however, the score is above the mean, then the z-value will be positive. If the score is the mean, then the z-value will be 0. The z-score and the mean in this case are identical. Time to see how it works. Assume you have a set of scores in which the mean is 67.75 and the standard deviation is 23.16. You want to standardize or convert to a z-score 95. 95 then is the raw score, or the score before we standardize it by converting it to a z-score. The first thing you do is plug everything into the equation, starting with the numerator. The score you're interested in, x, is 95. Subtract the mean from that, which is 67.75. Now hold for a moment. Notice that the score of 95 is greater than or exceeds the mean of 67.75. That tells us that once we finish calculating the z-score, we should have a positive number. Then plug the standard deviation of 23.16 into the denominator. If we do the calculation for the numerator, 95 minus 67.75, we come up with 27.25. When we divide that by the standard deviation of 23.16, so 27.25 divided by 23.16, we end up with a z-score of 1.1766. Let's do it again. Now the mean is 89.81 and the standard deviation is 5.86. You are interested in converting a raw score of 84 to a z-score. The first thing you should notice is that the 84, the score you're interested in, is less than the mean of 89.81, meaning that the resulting z-score will be negative. So take the score, x, of 84 and subtract the mean of 89.81 from it, and you'll get negative 1.89. The denominator is the standard deviation, which is 5.86. Do the math and you should come up with a z-score of negative 0.3232. And one more time. Now the mean is 10 and the standard deviation is 0.23. You are interested in the raw score of 10. Hey, we don't even have to do the calculations, as the score we are interested in is the mean, so we already know that the z-score is 0. Do the math, however, and with the numerator equaling 0, the resulting z-score will be 0. Now that you've calculated the z-score, what does it mean? And for that, you'll need to have a table of critical z-scores, often called simply a critical value table or a standard normal distribution table. You'll notice that this table actually consists of two pages, one dealing with negative z-scores and one dealing with positive z-scores. So let's talk about how to read this chart, which is the first step to figuring out what it means. For this example, we'll assume a z-score of 1.1766. which is the first z-score we calculated in this video for the raw score of 95. We are really interested in just the first 3 digits, which, when rounding, are 1.18. So that's the first step. Round to the second decimal place. Then determine if the z-score is positive or negative so that we can consult the correct chart. Ours is positive, so we pull up the page with positive numbers. Then we look at the first 2 numbers in our z-score, which are 1.1. Consulting the chart, look down the z column, or the y-axis, on the page to find the 1.1. Then find the third number, the one in the second decimal place, across the top row. In this example, that would be 0.08. Look to where the row and the column intersect, which is here, where the number expressed as a proportion is 0.8810, or as a percentage, 88.1%. This is our critical z-score, or our critical value, often abbreviated as simply CV. One more quick example to make sure you've got it, where you calculated the z-value for a raw score of 16 using the mean of 66.75 and the standard deviation of 23.16. Your calculated z-score, I know you can do the math now, is negative 2.2349, which, when rounded to the second decimal place, is negative 2.23. As this is a negative z-score, that means we have to switch pages so that we can consult the z-score critical value chart that shows negative z-values. Looking down the z column to find negative 2.2, and then over the top row to find 0.03, we find a critical z-value of 0.0129, meaning the percentage is 1.29, or at about the first percentile. Okay, so what does this all mean? Remember that a z-score is equal to the number of standard deviations from the mean. Our original z-score, the one we calculated in our last example for the raw score of 16, was negative 2.2349. As our z-score is a negative number, indicating that the value is lower than the mean, we know that the score will be somewhere to the left of the mean. The z-score of negative 2.23 means that it is 2.23 standard deviations below the mean, or about right here. Now let's look at the critical z-score that we got from our table, 0.0129, which when converted to a percentage is 1.29%. This will be in the region to the left of the mean. Had the z-score been positive, this percentage would be above 50% and therefore would be to the right of the mean. This means that the original score could be plotted at 1.29%, meaning that only 1.29% of the scores in the distribution are lower than our raw score of 16, and that 98.71% of those scores, 100% minus 1.29%, will be higher than our score. If this were where your grade on an exam were plotted, you wouldn't be too happy that almost 99% of the class outperformed you on the exam. But if your calculated z-score was the first one we calculated for an exam score of 95, 1.1766, plotted about here on the positive side above the mean, the critical z-score of 0.881 means that 88.1% of your fellow classmates scored lower than you, and that only 11.9% of the scores on the exam were better than your score. Of course, this should be consistent with what you already know about standard deviation, that 68% of all the scores in a normal distribution are within 1 standard deviation of the mean, 95% within 1.96 standard deviations of the mean, and 99% of the scores are within 2.58 standard deviations of the mean. Let's circle back for a bit to the table of critical z-scores. Remember that, by definition, the mean is the 50th percentile, where half the scores in the distribution are higher and half are lower. If the raw score you are converting to a z-score is the mean, we used this as an example earlier, the calculated z-score will be 0. And you can see on this chart that a calculated z-score of 0 equates to a critical z-score of 0.5%, or 50%. One last point. You can also work this backwards. If you have a critical z-score of 0.8810, meaning 88.1%, you can search the table to find the associated z-score. Just look for the critical value of 0.8810, figure out where the rows and columns intersect, and you can figure out the first 2 numbers, 1.1, and the third number, 0.08, combined equal 1.18, the z-score associated with the critical value of 0.8810. Let's do it for another critical z-score, say 0.0749 or 7.49%. Here it is, right at the intersection of negative 1.4 and 0.04. So the calculated z-score associated with a critical z-score of 0.0749 is negative 1.44. Processing time. What is the formula for calculating a z-score? First, you take the raw score and subtract the mean from it, then divide the result by the standard deviation. The formula can use x bar if you're working with a sample or mu if you're working with a population. What does a z-score of 1.5 mean? Remember that the z-score tells you how many standard deviations away from the mean a score is and in what direction. So a z-score of 1.5 means that the score can be plotted at 1.5 standard deviations above the mean. Why would you want to convert a calculated z-score to a critical z-score or critical value? So that you can determine what percentage of the other scores in the dataset are higher than it or below it. I'm fairly sure now that with the formula and a calculator, you can easily figure out z-scores, as long as you have the raw score, the mean, and the standard deviation.